All right, now proving something is a linear transformation is a lot harder than showing something isn't. We're going to need to show that both vector addition and scalar multiplication are preserved under that linear transformation. And that means for every single value. Again, one thing I kept seeing is students were still choosing random vectors and just showing that it works for this one set of vectors. Essentially what you're saying is, hey, look, I figured out that 1 squared is equal to 1, which means that x squared has to equal x for all numbers, right? Like a single value does not prove something. So we cannot just use a vector of our choosing. We need to say we're choosing some vector from our domain and showing that whether I do the map or the scalar multiplication or vector addition before or after, we're going to get the same result, right? So we can choose two vectors and they need to be general vectors. So we'll use something like x, y from R2 and AB, samesies. And let's go ahead and do vector addition first. So I'm going to state what I'm hoping to show. I would like to show that if I do this vector addition first, that I get out the same thing as if I had done the map first and then done my vector addition. All right, so we've got this setup is saying this is what I want to show. And then however you want to do that, personally, what we've been doing in class is sort of working with one and then working with the other. A lot of students chose to just sort of go like this and be like, okay, let's do, in fact, I'll set it up more like this you all did. Let's just do this first, okay? If we're doing the vector addition before we do the map, we are now have this new vector x plus a and y plus b that we are using this map to transform, right? And so we're okay, well, I know whatever the first element was in my R2, this vector I was applying this map to, this pre-image, that we're going to go ahead and we're going to take that 3 times that first element. And then we're going to add 6 of the second. And then for the second, we have 5 and 4. It's a linear combination of these two pieces. So here's our resulting vector. Now up to us if we want to take this one step further. I personally don't feel like we really need to go any further than this. I think we can do the distribution in our heads that's about to occur. All right, so the other side of this is, okay, well, now I need to check, well, what if I had done the map first and then added the two results together, my two images, right, from my codomain? Well, in that case, we would have had a 3x plus 6y and a negative 5x plus 4y. I love that. We don't even have to really think. We're just copying down the map. And then for the second mapping of that second image here, of image of AB, I do have to do a little swap out, little action here, plus 6b, negative 5a plus 4y. I might like one more step to combine this into a single vector. So now we have 3x plus 6y plus 3a plus 6b all over, not over, but can't stop myself. Speaking as I'm drawing. All right, so a lot of y'all had this, but then you didn't have a really crucial piece, right? The whole goal of everything here is to show that these two results are equal. We needed something. It could be at the beginning if you had just had that statement. It could be now, ooh, look. Therefore, this is all true, right? The thing we were I'm going to keep doing that, right? That we have this thing that we set out to show is actually we're just so used to in math using the like hard brackets there, second in these things. All right, I can do this AB. I have no space. I'm shoving things in here. Don't like it. It's deeply upsetting to me. You know, I like things cute. So T preserves vector addition. Cute? All right, so we did some work. We said the two things were equal. A lot of y'all were missing the two things are equal statement at some point. And then we said, now Okay, what did that tell us? It told me that T preserves vector addition. You're going to do the same thing for scalar multiplication. A lot of you were a little sloppy here, and when you did your scalar multiplication, you didn't say like, okay, we're going to say for any C and R, right? This is some number from R. I've already said that XY is from R2, my domain, and now we want to show that if we do that scalar multiplication, if we do that scalar multiplication first, we'll get the same thing as if we do the scalar multiplication after the map. Right, this is what we want to show. Now, at this point, we could be a little slicker if we want. Maybe it'd be like, okay, I'm just going to run this down like a 2-column proof from like a geometry class. Let's do CX, CY, right? That's what this thing is equal to. Okay, and then that's going to be, oh, we know what the transformation, it was 3 of whatever the first thing was, plus 6 of the second. And then the second element's -5 and 4. All right, so there's our result if we do the multiplication before the math. All right. Now our goal is to show that this is the same thing if I do this afterwards. So first we do our map. We make it clear that that's what we're doing. 3x plus 6y, -5x plus 4y. And we leave our c outside of all that. And we go, okay, well, if I do scalar multiplication, I know what that means. I'll have c times all of this. And c times all of this. Boop. These two are equal, therefore we can say T preserves scalar multiplication. And then you know me, I love a final, lovely concluding paragraph. So since T preserves, oh my gosh, preserves scalar mults and vector addition, T is a linear transformation. I like to say exactly what we get to conclude and why we get to conclude it. It's sort of like how we finished our series test back in 151, right? We would say the series blah, blah, blah converges based on, and we would talk about the results from whatever test we had done. So there we go. That was our linear transformation example.